Welcome back. So in the last few videos, we have seen how to use graphs for designing or modeling problems and how that can be useful for solving many of the problems. In this video, we will be looking at graphs as a subject itself. Now, graph theory is a big subject in itself. It would usually take one whole course to study graph theory, at least even for the elementary purposes. So in one video I cannot do a good justice on graph theory, but I would like to go over some of the properties of graphs that can be useful for understanding how to attack graph problems. Also, we have already seen some of the examples of how to use graphs for modeling problems. We will be continuing to see more such examples in this video and in the next video. So to quickly recap, what is graph? So it's a set of vertices and a set of edges. Edges are basically pairs of vertices. And the graph is given by V, E, but V is the set of vertices and E is the set of edges. Now, these are some of the definitions I have always shown whenever I talked about graphs. Namely, if the edges that represent some kind of a binary relation is symmetric, that means UV is in the edge if and only if VU is in the edge, then the graph is called undirected. And sometimes for our purposes we might add a weight to the edges. Also, if there is an edge from U to V, we say V is a neighbor of U, and the number of neighbors of V is known as the degree of V. So pictorially, we have this set of vertices and these edges to give the undirected graph. We can have weights on the edges to have weighted undirected graph, and we can have directions on these edges to get weighted directed graph. We have seen the use of undirected graph as well as directed graph. We haven't seen the use of weighted graphs yet, but as you can imagine, weighted graphs can also be useful for modeling various problems. Now, the main advantage of graphs is that they are very simple and yet pretty general, and they can be used to design or model lots and lots of real life problems. And hence studying graph structures is an important field by itself. In this video, I will be going through some of the properties of graphs and try to convince you that those properties are correct. I will not be giving very formal proofs in any of those cases. I would really recommend you guys to take a full course on graph theory, which will be much useful for understanding the graph theory aspects. In the next video and the next couple of videos, we will be showing about how to model other problems using not only just graph theory but other mathematical objects, and you will slowly start to realize the importance of this object of graphs. So there are a number of properties and structures in the graph that arise again and again, and we need to study them by themselves. So the idea is that the theory should be there so that whenever we convert the problem to graphs, we can use properties from the theory to answer the problems. Right? So to start with, we looked at the concept of paths. So a path from U to V is basically a sequence of edges that start from a vertex sequence of vertices that starts from U and end at V, so that any consecutive vertex has an edge between them. So in other words, if I have this is the graph and I want to draw a path from G to A, GFDA is a path. So is GECBDA is a path. Now if the graph is directed, then we have to talk about a directed path. So if this is the direction on the edges, then this GECBDA is unfortunately not a directed path because the edge between B and D is in the wrong direction. So this is not a directed path, but something like GECBA is a directed path from G to A. Now if there is a path from U to V, we say U is connected to V. In an undirected graph, if for any two vertex U and V it is connected, then we say the graph is connected. And as you can see, since in an undirected graph there is no direction, if there is a path from U to V, there is a path from V to U also. Now, here is the first problem that we had asked you to think about, namely, this relation U is connected to V is an equivalent relation. Now, let's try to prove this particular case. So, if this is the graph G, first of all, to prove that it is equivalent relation, we have to solve three things, namely, it is symmetric, reflexive, and transitive. Now, first of all, it is reflexive. Why? Because U is related to U. So, U is connected to U because you start from U, you are always in U, so there is a path from going from U to U. So, this vacuous is true that U is connected to U. So, I have to prove reflexive, symmetric, and transitive. Now, reflexive is easy. What about symmetric? Now, if there is a path from U to V, now by the way, this one I had pointed out last time also, here we mean that the graph is undirected. The graph is undirected, so there is a path from U to V, right? So, if this one is, as we have denoted, V1, V0, V1, V2, V3 till Vk. Now note that we can also have a path from V to U by then renaming this one as V0, the next one as V1, till this one as V3. So U is connected to V, that means V is connected to U. So it's kind of easy to see that they are symmetric. So symmetric case also true. Now what about the transitive case? So the transitive case, the idea is that if U is connected to V and V is connected to W, so it may be that V is connected to W through this path. And this is W. So there is a path from U to V, there is a path from V to W. It may be that some of the edges are used, some of the vertices are used. Now question is that is there a path from U to W? And the answer is that yes, it is. For example, I can therefore then traverse go from U to W by going to U to V and then retracing back the path and going back to W. So if there is a path from U to V and there is a path from V to W, then there is a path from U to W also. Hence, in the case of undirected graph, it is an equivalent relation. Now, why did we use the undirectedness? No, the undirectedness was specially used for the symmetric case. If it is not undirected, then the relationship is not symmetric. Okay? So that means if the graph is undirected, then the relation, namely u is connected to v, is an equivalent relation. And when we have an equivalent relation, as we have pointed out then earlier, then the whole set on which the relationship is told, namely the set of vertices here, we can split them up into equivalent partitions, right? So namely, we can therefore split up the graph G into chunks like this, where any two vertex here is related. Any two vertex here, all the vertices are related, and a vertex from this point to this point is not related. So, so we have the equivalent classes. These are the equivalent classes, and what it means is that these are all connected graphs. Somehow means you can go from any vertex to any vertex, but you cannot go from one connected component to the other. These are called the connected component. So thus, if the graph is undirected, then the whole graph can be split up into connected components, where individual components are connected, and across components there is no way one can go from the other one to the other. Note that this heavily uses the fact that the relationship is equivalent, and in fact, if the relationship is not equivalent, then we could not have got it, and hence, if the graph G was not undirected but was directed, then we could not have got this particular property. So we have this. So an undirected graph we can split up into connected components, and the graph is a disjoint union of the connected components. This is both the case of undirected graph. Now moving on, there is a concept of cycles, which is basically a path that starts and ends at the same place. So for example, this is a cycle, G, F, D, P, E is a cycle. So is this one, D, A, B, C, D, A, B, E is a cycle. And we can also have directed cycles. For example, this is not a directed cycle, but this is a directed cycle. Right? So cycles are very useful concepts in graph theory. And here is one of the nice problems that we have. That if G is an undirected graph such that every vertex has degree greater than 2, greater than or equal to 2, then G has a cycle. What does it mean by every vertex have degree greater than or equal to 2? Meaning every vertex have 2 neighbors. So let's see how to prove this statement. So if this is a graph, what we can do is that we can start from a vertex and keep on walking on the edges. Right? Now, if I keep on walking on the edges, because every vertex have degree 2, greater than 2, that is whatever edge I enter from, I will try not to go out from that same edge. So I enter a vertex from an edge and leave a vertex from a different edge. Because of the degree 2 case, every vertex has 2 edges going in, 2 edges adjacent to it. So what I do is I start from a vertex and keep on walking. I enter a vertex from an edge and leave the vertex through the other edge. Now, I cannot keep on going about it infinitely, right? Because the graph is finite. So at some point of time, I must end up coming back to one of the vertices I have already visited. And once I have that, I get a cycle. This is a cycle. right? So let's try to prove it again by looking at a graph which does not have a cycle. Say for example this graph does not have a cycle. Now here thing is that if I start walking from here, I could have been here, then go here, then go here. But now I have to retrace back my path on the same path, which is unfortunately what I don't want to do. Right? So it is very important that we, whatever age we enter from, we don't go out from the same path in this cycle. By doing so, we can ensure that we always, if I end up revisiting a vertex second time, we actually get a cycle. Okay, so this is a very simple, quick observation, and that's a very powerful observation, as we will see very shortly. What does this particular observation mean? That if a graph, if every vertex has degree greater than or equal to 2, then the graph has a cycle. Note that we can have a graph like this, in which case, as you can see, every vertex except for the first and the last has degree equal to 2, and yet it does not have a cycle. So we always require that every vertex has degree greater than or equal to 2. We require that. Right? Now we have the concept of trees. So what is a tree? First of all, a graph that does not have a cycle, an undirected graph that does not have a cycle, is called an acyclic graph. And if that acyclic graph is connected, then we call it a tree. Now why is it a tree called? So it's basically because if you draw a graph of this form, it is usually like this. So this is the typical representation of a graph that does not have a cycle. Okay. So as you can see, it looks like a tree, and therefore it is called a tree. Sometimes it is drawn in the opposite direction. So it is drawn like this. So if this is a graph, for example, then we can have this is a tree. A tree where is a connected graph, the red edges gives you a connected graph, and there is no cycle. So it's a tree. Similarly, this is also a tree. Right? There can be various kind of trees. So the definition of the tree: if a connected undirected graph that does not have a cycle is called a tree. Now here is an equivalent definition of a tree, namely a tree is minimally connected graph. Now what does it mean by minimally connected? So graph is minimally connected if I can remove, for example, that this is a graph, and I say that this is not a minimally connected graph. Why? Because I can remove this edge and still the graph can be connected. So graph is minimally connected if I cannot remove any edge, and yet if I remove any edge, then the graph becomes disconnected. A graph is minimally connected. Now the thing is that if a graph has a cycle, then the graph cannot be minimally connected. So if this is a graph and there is a cycle sitting here, and I don't care how things are there otherwise, but in this cycle I can take any of the edge and remove that, and yet the graph will be remain connected. So this is not a minimally connected graph because I could remove an edge and still the graph could remain connected, right? So as you can see, I just now proved to you that if a graph has a cycle, then the graph is is not minimally connected. Now, how do I prove the opposite direction? If a graph is not minimally connected, it must have a cycle. Okay, I leave it to you guys to think about it. But basic idea is that, most important thing is that a tree has 2 or 3 different definitions, all of them are equivalent. This is one of them, that this is a connected graph that doesn't have a cycle. And second one is this one, a tree is the minimally connected graph, meaning given a graph is minimally connected if by removing any edge you can make it disconnected. If it is not that case, then it's called minimally connected. Now, here is one very important property of graphs. A tree has a degree 1 vertex. Now, can someone see how to prove this statement? We prove it by contradiction. So, if this is not the case, that means what? That means all vertex has degree greater than or equal to 2. And if that is the case, then we just now proved some couple of slides ago that it means that the graph has a cycle, which means that graph is not a tree by the definition. So, a tree must have a degree 1 vertex, at least one degree 1 vertex. If it doesn't have any degree 1 vertex, then it must have a cycle, and in that case, we contradict the definition of a tree. So once we have such a vertex, we call that vertex a leaf. Now how does this leaf look like? Let's say I have the graph G, this is a tree, right? This is a tree, and I know that there is a vertex like this, a vertex of degree 1. Now what does it mean? That means this tree has lots of other things like this. Now, what happens if I remove this vertex? Will the graph remain connected? If I remove this vertex as well as this edge? The fact is that yes, it will remain connected. Why? Because any path from say U to V cannot use this vertex, because it must be going via path without using this vertex. So if I remove this edge, no pair of vertex is disturbed. The only pair of vertex that gets disturbed is the path from this particular vertex to any other vertex. But given the fact that I have destroyed this particular vertex, so the rest of the graph is still connected. So I get this following, that if you remove the leaf from a tree, the tree still remains connected. So here note that I am not just removing the edge from the leaf to the rest of the tree, but the leaf itself. So I get a graph on a smaller number of vertices, right? So for example, if this is a tree, and if I remove this edge and this vertex, then I get this graph. This is a graph on one less number of vertices, but still it is a tree and still it is connected, right? This is an important note observation, that if you remove a leaf from a tree, then the rest of the graph is still connected. Now, can you answer this question? How many edges are there in a graph on n vertices? Now, to answer this one, let me say that, okay, let me first give you the answer. The answer is n minus 1. And how do you prove it? Now, the proving can be done by induction. So, here was a tree and here was a leaf. A tree always has a leaf, right? So, this is the graph on smaller, so this is a tree on Tn minus 1. And this whole thing is a tree on n vertices. So how many edges are there in this tree on n minus 1? Note, number of edges is on this set is by induction hypothesis is n minus 2. And how many edges are there in Tn? So this is number of edges in Tn minus 1. Right? Number of edges in Tn minus 1 plus this edge plus 1, which is Tn n minus 2 plus n minus plus 1 is n minus 1. So basically, by using induction, one can prove induction and all the other properties that we have used. So what are properties we have used? We have used the property that a tree has a leaf, okay, or a degree 1 vertex, and we have also used that if you remove the leaf from the tree, you get a tree on a smaller number of edges, vertices, right? And then we apply the induction hypothesis on this particular case to get the answer that the number of edges in a tree on n vertices is n minus 1. Now I would request you guys to go and solve this particular induction completely for yourselves. In this course, it will be hard for me to judge whether you have understood the induction techniques, how well you have understood the induction techniques, particularly because the quizzes and assignments are all multiple choice questions, which are not the most perfect way of judging the understanding of topics like induction hypothesis. But this is a good example. How many edges are there in a tree on n vertices? A good example where you have to do induction on graphs. This is a very important concept. We have done induction on graphs earlier also, particularly in the case of the tournament problem and so on. But this is something very useful and very crucial for your understanding of graph theory and induction. Right? Okay, now moving on. Other than trees, we also, there was this concept of spanning tree. Now, so given a graph, if we remove some of the edges and some of the vertices, then whatever we get, we call it a subgraph. Now, given a graph G, a tree that is a subgraph of G and touches every vertex is called a spanning tree. Now the question is that every graph has a spanning tree as a subgraph. Now this follows from the fact that if this graph is not already a tree, so first of all, if the graph is already a tree and the graph is connected, then the graph itself is a spanning tree. If the graph is not a tree and is connected, so that means it is not minimally connected. In that case, there must be a cycle or an edge that I can remove. So I remove that edge, I get a smaller graph which is connected, and we recurse on that again. So using this recursive idea, we do get the fact that every graph has a spanning tree as a subgraph. Now, other than the trees and paths, we also looked at things like independent set and clique. Now, these are two very important concepts again. An independent set is a set of vertices such that no two vertices in this set has an edge between them. And a clique is a set of vertices such that there is an edge between any pair of vertices in this set. So for example, if this is an if this is a graph, the independent set is this one, say A and E, because there is no edge between them. Or D, C and G forms another independent set. On the other hand, say C, F and G is a clique of size 3. Similarly, we can have A, D and B is a clique of size 3 again. Now, finding the largest independent set or the largest clique in a graph is a pretty complicated or a hard problem, a very challenging problem, very well studied problem also. So we have seen the application of independent set. I am going to skip this case. Let me go on to a different concept, namely the coloring. So given a graph G, a coloring is basically coloring the set of vertices using colors, namely there is a mapping from the vertex set to 1 to k such that no two consecutive edge in a vertex has the same color. That means if there is an edge between Vi and Vj, then color of Vi is not equal to color of Vj. The typical question is that can one color a graph with k colors? Right? So in this case, the minimum number of colors required to color a graph is called the chromatic number of a graph. So for example here, if this is the graph, if A is colored red, B is colored blue, C can be colored red again, D because it's adjacent to both red and blue can be colored green, E because it is adjacent to all red, blue and green, it has to be colored yellow, and F can be colored red and G can be colored green, and here we have a coloring with 4 colors. Now, can you color this graph with less than that? Namely, can you color this graph with 3 colors? This is the kind of question that usually is asked. And we have seen that the application of coloring can be seen in the coloring of maps. So for example, here is coloring of the states of India using colors so that no two adjacent state has the same color. And as you can see, it uses 4 colors. Now, let me just tell you here, I cannot prove it, that every map can be colored with 4 colors. So every map can be colored with 4 colors. This is called the 4 coloring theorem, and a very beautiful theorem. Unfortunately, it is beyond the scope of this course to tell you the proof of this theorem. but I encourage you to go and take a look at it in some other place, maybe online or something. There you will find the four coloring theorem. Now here is one very nice thing. So if every vertex of a graph has degree less than d, then the graph is decolorable, meaning the graph can be colored using d colors. Now why is it so? Again, the way to prove it by induction. To take a graph G where every vertex has degree less than or less than d, take a vertex V and let's consider G minus V, right? Now this is G minus V. Now G minus V is again a graph where the degree of every vertex is less than d, because if you remove a vertex, the degree cannot go up. So without loss of generality, or rather by inductive hypothesis, I can assume that there exists a decoloring of this graph. There exists a decoloring. Now consider V. Question is that what do you color V? Now V has how many neighbors? It has less than d. That means at most d minus 1 neighbors. So that means there must be d minus 1 colors that the neighbors have. So if I have any of the d colors, one of the color must be missing from the neighbors. I can use it to color vertex V, right? And hence I get a decoloring of this whole graph. So if all the vertex of a graph has less than d colors, then the graph is decolorable, right? So this is a very, again, a nice property that would come in handy many times. And using this one, actually, you can prove that a map can be colored using 4 colors. A map can be colored using 4 colors. Sorry, not 4, 5 colors. 4 color is slightly hard, but 5 color is easy. So you can get this proof using this particular theorem that I have proved. I leave it to you guys to go and check the proof of this whole thing. Now, one more problem on coloring. So if alpha G is the set of independent set and this chi G is the chromatic number, meaning number of colors required to color the graph, then prove that the product of them is greater than the size of the graph on size of V. Now why is it so? Let me quickly, it basically follows from again the definitions. So if I have a coloring of this graph, say, so this one I can color red, this one I can color blue, this one also I can color blue, this one I can color red, this one I can color blue, this one I can color black, we have made a mistake here. This is not the best coloring. The best coloring to do is be this one colored blue, this be colored black, then this can be colored black, and this can be colored red. Now note that if you look at the red colors, the vertex colored red, then they don't have an edge between them. This is by definition, right? That no two red colored vertex can have an edge between them, because no two vertex which are adjacent have the same color. So that means the red colors is an independent set. Similarly, as you can see, the blue colors will also give you another independent set. And similarly, the black colors will also give you an independent set. And by definition of this is the maximum independent set, that means the number of vertices colored red is less than alpha g. The number of vertices colored blue is also less than alpha g. Number of vertices colored black is also less than alpha g. So the number of vertices colored is less than the number of colors times alpha g. So namely number of vertex, therefore we have the size alpha g times chromatic number is greater than or equal to the number of vertices. So here is another problem or property of graphs that can be solved not using induction but just by plain definition, on the plain definition, right? Okay. So what we have till now, we have the fact that graphs are very useful for modeling various problems. The graphs are studied by themselves in a subject called graph theory. We have studied some of the properties of graphs, and most of the properties can be deduced using the similar proof techniques, namely induction, contradiction, case studies, etc. Now this is clearly not the end of graph theory. Graph theory is a huge subject in itself, and we will not be able to spend too much time on graph theory. But I hope that you have understood the importance of graphs and how that can be useful for modeling real life problems. In the next few videos, I will be talking about modeling in general, taking a problem and modeling it into some other mathematical things. Particularly, I will be looking at something called linear programming and graph theory, and see how problems in real life can be modeled in linear programming and graph theory. Thank you.